We have exactly 4 people here with us today. I'm just letting the people watching the video know that there are 4 of us. Still 4. But it is 1 o'clock and we begin. Because of the weather, I know that there's at least one person who is not able to make it to our class and emailed me. I'm hoping more people trickle in. Officially, the school closes at 3 o'clock today. So any class that starts at 3 o'clock or later is canceled. The buildings will close at 3 o'clock. Everything shuts down at 3 o'clock, okay? All right, even with 3 people or 4 people, 5 now, well done. We'll go ahead and get started. So we're on page 7 in the packet. I was going to talk a little bit about some of the feedback that you guys gave me on the survey. A bunch of folks filled this survey out for me, but I'd like to talk about the feedback that I got when we have more people here. So we'll come back to this. I've also got this piece of paper where you are going to decide how you want me to grade how you want me to give you a grade at the end of the semester. So just find your name and circle the grading choice that you are interested in. And today we talk about this idea of linear regression, and it's going to kind of follow nicely from our equations of lines day. Welcome. Come on in. Here's the nutshell version of what happened last class. Given 2 points, find the equation of the line that hits those 2 points. That's what we did last class, right? Find the equation of a line that satisfies blah. And what happened with all of the equations of the lines that we found last time is that they were perfect, meaning if you had 2 points, you can find a line that perfectly hits all of those points. Agree? But today we're going to see some examples of maybe more than 2 points, like 3 or 4 or 10 points. And maybe it looks like they're kind of close to being on a line, but maybe there's no single line that hits all of those points. And if you can't find a single line that hits all the points, we could maybe talk about finding the line that's closest to all the points. The best fit line is what we call it. And that's what today is all about. So let's start on page 7 here. And we will go to number 1. And we'll start with Eric.
In mathematics, we are often using the value of variable. We predict the value of, for example, what year it is in the population of Miami in that year. Increasing or decreasing.
What do you guys think? As time passes, do you think that the population of Miami is going up or down, or maybe it changes depending on when we are? A couple of folks think up. Seems like Miami is still growing. It doesn't mean that every city is growing. For example, Detroit's population has really, really dwindled in the last few years. So not every town is growing in population, but maybe Miami is still growing. So we'll go to number 2 for Matt. You can just read it off the board if that's all right.
This table gives the population of Miami.
Okay. How often do we have a census here in the U.S.? Every 10 years. I have not given you all the numbers. This is just a few of the numbers from the censuses for the population of Miami. Looking at the population of Miami throughout the years, do you see whether it's an increasing or decreasing relationship? It's pretty clear that it's been increasing. Is it also clear, do you guys agree that, that there's a couple of different possibilities for how something can increase? So I'm thinking about a graph. Time is over here. Population is here. Here's one way that something can be increasing. Every year, another 2,000 people go to Miami, and that's what it would look like. But that's not the only way something can increase. This is another example of something that's increasing. From this year to this year, did you gain a lot of people or not that many people? Not that many. It didn't go up by much. But from that year to, say, over here, like here to here, we gained more people than we did in the previous jump. And then if we move over, I'm trying to like move over the same horizontal amount every time. So maybe out here, and you can see that it feels like we're gaining even more people the next year. So that town would be increasing faster and faster and faster. And then there's even a third town where it's, what is it doing? Is that increasing or decreasing? That's increasing the whole time. In the beginning, it's quite steep, meaning you have a lot of people coming in every year in the beginning. But then fewer and fewer, still getting more people, but you're not getting as many. So maybe like this year you get 10, next year only 8 new people come in, next year only 5. So still increasing, but smaller and smaller. And maybe, what word did you use, Eric? Maybe it's kind of plateauing. Maybe there's some limit and we won't have more than 1 million people in the town. It just won't support it, okay? Looking at the points, would you guys agree it's kind of hard to tell which one it is? Just looking at these numbers, it's hard for me to know, did I keep gaining the same number of people every year, which would be like this black line, or was it growing slow and then fast like purple, or was it growing fast and then slow like green? Just looking at the numbers, it's kind of hard to do that analysis, right? So what would be a better way to see it? Well, it's actually to see it, to plot the points. Let's take a look down here at number 4, and we will go to Sam. Okay, this is a screenshot from your calculator. At the end of today, I will show you how to do all this stuff on the calculator, but first thing I want us to be able to do is analyze the results. So I've just plotted the 4 points that are up there in the table. I want to know which one corresponds to this population here, 1950 and 250,000 about. So just looking at the graph on the left, you can't say anything because you don't know what the hash marks represent. So we got to look at the window as well. So the window says 0 to 120 by 10s. So that's 0, that's 10, 20, 30, 40, and 50 is this one right here. And it feels like maybe that's what we're talking about when we say 1950, is that 50. And let's see if that matches up on the vertical. What's the top number on the vertical? 450,000. And what do these hash marks count? Every 100,000. So starting down here, that's 100,000, 200,000, 300,000, and then 400,000 plus a little space up above. So this point right here seems like it could be about what? About 250,000. So is everybody okay, you know, kind of labeling this point? That's 50 and 250,000. Okay, and again, what is that plot called? That's a scatter plot. So named because the dots could be everywhere and it could just look like they've been scattered on the plot. Okay, if I'm being honest, I have no idea if that's why it's so named, but it makes sense to me. And if I stand up here and say something like firmly enough, you'll believe anything I tell you. So let's just say that's why it's called scatter plot. Okay, number 5. Oh, and again, for the people that came in late today, because of the weather, GCC is closing at 3 o'clock. It won't affect us, but if you have class starting at 3 or later, it is canceled and the buildings will close at 3. Drive really safely when you go home. Okay, let's try number 5. We'll go to Hazen. Okay, so increasing or decreasing, looking at the dots, what is it doing? Increasing, it's clear. I guess it was kind of clear looking at the numbers too, but it's sure a whole heck of a lot easier for me to look at the dots. And is it fairly close to linear? Well, I mean, it doesn't look like a straight line, but you know, I could maybe draw something that's a straight line that's close to all 4 points. So, you know, fairly close to linear. It's definitely not perfectly linear, but I don't know, close enough, I suppose. We'll go to 6, Megan. Okay, let's figure out what that means in this context. So larger values of one occur with larger values of the other. This right here is a large value of what? What variable is down there? It's time, it's years. And what variable is over here? That's population. And was it true that they both were big at kind of the same point? Yeah. And said another way, positively associated just means increasing. That's all that it means. So we'll translate. We'll just say that this just means increasing, and this one just means decreasing. But then we'll say one more thing about why maybe we call it positively associated or negatively associated. Do you guys remember, what can you tell me about the slope of that green line? What kind of a number is that slope? It is a positive number because that is an uphill line. Remember, we always run to the right. And if we are running to the right, we are getting out of breath because we are going uphill. And we know that uphill lines have positive slopes. So when we say positively associated, we're really just saying positive slope. So that's the connection to yesterday. It's a positive slope. Negatively associated means negative slope. All right, so when we're ready, we'll go to the next page. Number 7, Serge. Okay, so what do we think? Is that a positive or negative association for Miami? Positive, positive slope. Okay, we'll go to 8 for Tyler. Okay, let's pause right there. If the points are really close to all falling on a line, then we would say that is a strong association. If the points are all kind of far away from the line, that is a weak association. And maybe a line is really just not appropriate at all to use. I will show you a picture. You don't need to skip ahead, but for example, let's look at this picture here in the middle. Look at the dots. Would you say that this is like close to being a linear relationship? No, it's very much not linear. It's about as not linear as we could maybe imagine. Still, I can draw a line that is the closest to all of those dots, but the fact is it's just not very close. So would we call that a strong or a weak association? That is a weak association, all right? So if it looks like the points are fairly close to a line, like that one, then it's a strong association. But if they're really not close at all, it is a weak association. And the reason we care about that is that if you're trying to like predict where the dots should be and you have a weak association, well, your answers are going to be really far from reality. But if you have a strong association, then maybe you can predict where some other dots are going to be because you know they'll be close to the line. Tyler, can you keep going? Andy? Okay, and can you read the sentence right above that one too? Okay, so I'm defining a number that's going to tell you how strong or weak your association is. And the number doesn't have any meaning yet because you've never seen these numbers, or maybe you've never seen these numbers before. I will tell you, if the association is perfectly uphill and all of the points fall exactly on a line, then I'm going to say that that has the number 1. So if you see a 1, it means it's perfect. If they fall on a line but it's downhill, it's going to be -1. So the perfect examples are either going to be +1 for uphill lines, -1 for downhill lines. Everything that isn't perfect, a set of dots that don't fall perfectly on the line, they're all going to be between -1 and 1. If they're close to these extremes, it's a strong association. Anything close to 1 or close to -1 is a strong association, which means numbers close to what are weak. Anything close to 0 is a weak association, okay? So the two extremes are the perfect lines, and the closer you are to 0, the weaker the association. And so for the population example, as Andy read, the number was 0.95. Is that strong or is that weak? That's strong. 0.95 is pretty darn close to 1. So looking at this line that I drew here, I just estimated it, but you know, like that, those points aren't all that far from the line. I guess I'd be happier if the number were not 0.95, but rather were 0.99. That would be stronger. But anyway, that's what a 0.95 looks like. Okay, we're going to Matt again for number 10. Eric?
For example, shoe sizes strongly correlated with practicability.
Okay, so this is perfectly true. Children with bigger shoe sizes are better at math than children with small shoe sizes. There is a very strong relationship, a very strong correlation between the size of your shoe as a kid and how good you are at math. Would you agree that having large feet makes you better at math? No. What's the underlying?
A causes B, its case of C causes A and B.
So what's the C that Iris is talking about? Yeah. Like age is the thing that's underlying everything, right? As you get older, what happens? Your feet get bigger and you get better, well, you know more math, right? And so it's really dangerous. Just because you have a good relationship like this 0.95 is fairly strong, doesn't mean that one thing is causing another. It could be they are both related to some underlying third thing that we haven't been studying. So it's a little bit dangerous to make conclusions. But anyway, just something to point out. Iris?
The thing to remember is that where there's a correlation between variables A and B, there are possible explanations. A causes B causes A, or C causes A and B.
Makes sense to me. Okay, we'll go back to Iris for number 11.
Linear regression, or disparate regression, is a formal mathematical model used to describe the relationship between variables. In our example, we'd like to fit the population of Miami in any given year. Simplest rule of the time is to assume that a straight line describes this relationship.
Okay, so let's come back to this picture that we have here. I've got data collected from the census, and there was a census in 2010, so we have more data we could think about. But do you think that maybe there's some trend happening here that perhaps I could try to predict the population of Miami in 2020 without waiting until 2020 gets here? And folks do this all the time when we talk about budgets and trying to plan for Miami's fiscal future. They have to try to estimate how many people are we going to have to take care of here in terms of all of our services. So certainly it's in our best interest to try to be able to predict stuff that hasn't happened yet. And if I believe that the points here are all kind of close to a line, then I could maybe find the equation of that line somehow and then like plug in 2020 into my line. And that would give me a point that's on the line that would hopefully be close to the expected population of Miami in the year 2020. This is the goal. This is why we care about regression. It's the ability to predict information that you don't have yet. We're making an assumption. The assumption is that the points are going to keep trending the way that they are. So there's always a danger that something drastic could change. You know, the population of Miami might not continue that trend. But anyway, that's the goal. Are we clear on why we're doing this stuff? Okay. So we're going to go to Eliza, our goal. Megan? Okay, so here's some screenshots for that same population example. I drew a line before. It turns out this is mathematically the best line that exists. I will show you how to get the calculator to do all of that. But first I want to be able to analyze what we're looking at. So let's take a look. We are trying to do 14 first. Oh, and by the way, you see the R is the 0.95? Like your calculator will tell you that if you ask for it. So 0.95 is close to 1. That's a pretty good fit. We're up to Hazen for 14. Okay, so look at the screenshot on the top right. It says y is equal, first it says linreg. What does that stand for? Linear regression, that's what we asked the calculator to do, and this is what it spits out. Y equals ax plus b, that's the equation. It's telling you what a and b are. So all we have to do is fill in. Y equals, instead of a, what number are we putting? 35, 44. According to the equation, what do you put right next to the a? You put an x. Plus. Instead of the b, what do we put? 36, 9, 43. We'll just round. First, is it clear how to get that equation? R squared is actually just, we didn't talk about it, but it's just the square of this number right here. So like 0.95 squared is this 0.90 stuff. It turns out that, excuse me, in statistics, there's like you do certain things with the R value and then you analyze other information with the R squared value. I think that actually for most, if we're not looking at a line, but if instead we're looking at like a curvy thing, I don't even know that R exists, but R squared will always show up on your calculator. For us, we're just looking for numbers for R that are close to 1 or minus 1. Okay, and one thing I want to do, I'd like to analyze this equation. What does that 34, 35, 44 mean, and what does that 36,000 mean? But in order for me to do that, I'd actually first prefer to change the x and the y. X represented what in this problem? Was years, was time. So how about we just kind of cross that off and change it to a t. And the vertical axis, normally it's y, but what was it in this problem? It was population. I'm going to cross that off and make it p. Okay, so the first thing we want to do here is, we got Hazen or Sam? Go ahead, Hazen. Okay, so let's think about the slope. So first of all, which number is the slope? The 35 or the 36? Okay, so slope is 35. It's the number touching the variable, the x. Okay, in order to talk about the slope and writing a sentence about the slope, I think what we'd like to do is get the units. 35, 44. Somethings per something.
Persons per year.
Yeah, so remember I think we wrote something down the other day that was like the units for the slope are whatever the units are for y divided by whatever the units are for x. We wrote this the other day, didn't we? And I hope it makes sense because slope is change in y over change in x. So the units I think are in the right spot. All right, we don't really have y, we have p. So what were the units for p? It was people. So this is people. And then on the bottom go x units, but it's not really x, it's t. What was t measured in? Years. So that 3544 as a standalone number, I don't have much meaning for it. But put units on it, and I've almost got the interpretation without doing any more work. 3,544 people per year. You really just have to write like a couple of words in that sentence, and you've got your interpretation. What's happening in Miami? What's happening with that 3,544 people? We are gaining, right? We are gaining 3,544 people per year.
And a test would be happy with both X's.
Mm-hmm. Yeah, I write the first thing down to help me get the second thing. Other questions on the interpretation? How would I know that it was a loss instead of a gain of people? Yeah, if that slope had been a negative 3544, then we would say we're losing. But if it's positive, we are gaining. Is it true that every year Miami gained 3,544 people? No. Yeah, I mean, like here, we're using a line. to try to estimate discrete points, like 4 points were up there. And we're just trying to hit them as close as we can with a line. So there's an average type thing happening here. Roughly 3,544 people were gained per year. I don't even think Miami could tell you in a single year how many people came into the city. It's hard to count how many people live in a city. Like at this moment in time, I don't know what the population of Greenfield is, and I'd imagine that nobody knows what the population, and we're a small town.
Well, number of permanent residents with established residences is pretty well known. You never know how many people are coming into the city to shop or to something on any day.
Yeah, but I'm not even, it's a good point, but I'm not even talking about the people, homeless people enter into it, right? I mean, there are homeless people that live here in Greenfield, and I don't imagine anybody knows exactly how many of them there are. Oftentimes, immigrants are undercounted with census data because there might be a fear of filling out any kind of government form that, you know, like if you're, if you're illegal and you're worried about being deported, certainly you're not going to fill in any census information. So there are a lot of reasons why people are not accurately counted. So certainly this is just an approximation. Next page, Sam. Okay, so the y-intercept in this case was the value of b. What is the y-intercept? 943. And I will say that something is special at every y-intercept, not just for this equation, but how do you get to be on the y-axis? You need x to equal 0. And I think I mentioned if you give me a sentence about a y-intercept and the 0 is not in there somewhere, then you've missed the boat. Okay, I'm going to change it though. We don't have x. What do we have? We have t. Okay, so the y-intercept is 36,943 when t equals 0. I'm going to go ahead and cross off the b as well. B is like a y-intercept, but it's not y. What is it? It's really p. So if you just cross things off and put the right letters, again, you're almost all the way to the sentence. When time was equal to 0, the population was 36,943. But time equals 0 is not really an English phrase. So if we looked at the graph and we figured that this 50 wasn't really year 50, what was it? It was 1950. Then what year is year 0? Is 1900, okay? So in 1900, we're trying to say that perhaps the population of Miami was 36,943. Questions on the y-intercept interpretation? Okay, we'll go for Serge again for 17. Okay, can somebody remind me of the equation? It was 34 and then plus, what was it? 30. Oh, that's my fault. Okay, 3544. Okay, so there's our equation. We're trying to use the equation to predict the population. Which letter am I after? I want P, predicting the population. What do I know? I know T, 2009. If you plug 2009 in, you're going to get some incredibly wrong number. 2009 is the year, but remember T was since 1900. How many years has it been since 1900? 109. Be really, really careful that you don't just naively plug this in as 2009, because you will be predicting the population in the year 3,909, which is not what we're after. Okay, so we got 3544 times this 109 plus the other number. So somebody with a calculator, can we crunch this through? Thank you. So if Miami stayed on that trend, that line, then the population in 2009 would have been 423,000. Okay, who's our reader now? Are we back to Tyler? According? Right above 18. $399,000. Okay, thank you. All right, so how was our prediction? We predicted 423,000. The right answer, it turns out, was about 400,000. Okay, did we over or underestimate reality? We overestimated, and by a pretty significant amount. I mean, 20,000 people out of 400,000 people, that's a lot to overcount by. But perhaps we could have predicted that that was going to happen because, well, not only do the data not seem to fall on a line, but if I were to just try to connect these with a smooth curve, if I don't restrict myself to a line, I kind of feel like what's happening in the last, 30 years, it's not growing as fast as it was in the earlier part of the 1900s. And so what we did here, let's see, counting boxes, 10, 20, 30, 40, 50, 60, 70, 80, 90, 2000 is right here. And then 2010 is out here. And so what we tried to do was go to 2009 and use the line to predict the population at 420,000. That's what we did. But in reality, it didn't even look like Miami was heading along that line by the time we got there. If I were to continue the red just a little bit, then it seems like maybe something a little bit under. So we used the best line we could, flawed as it was, and we ended up overestimating, and we're not surprised. We overestimated. Is that a question? Stretching. Mm-hmm. Yeah, so this is just an aside. Statistics is not my area of expertise, but I will share with you just about everything I know with R and R squared. And none of what I'm saying in these next few sentences is like on a quiz or a test. But R squared, actually, I think, is a percentage. So looking at R squared, which is 0.90, what percent is that? 90%. So here's the idea. There are a lot of factors that go into why Miami's population changes from, like from one moment in time to another. Of course, time is passing, and that's one of the factors. But there are lots of other reasons that Miami's population might grow quick or slow or might even decrease. And the idea here is that time passing explains 90% of the reason Miami's population is doing what it's doing. That R squared right there, that 90%, is saying that 90% of the increase in Miami's population happens because time is passing. The other 10%, other stuff. Maybe people are scared away by pollution, or maybe there's a lot of crime happening, or maybe there's a lot of people going there because they, generally the average age in Florida is what compared to like in the rest of the country? It's generally higher. So a lot of senior citizens end up going to Florida to retire. Well, you guys know about like baby boomers, right? And so that whole generation is now like nearing retirement age or at retirement age. So maybe Miami's going to see an influx of people just because there are a lot of people that happen to be like around 65 years old. Well, it has nothing to do with the calendar year passing. It's just kind of like a sociological type thing that happened, back when the baby boomer generation started. So that's about all that I know. 90% of the reason for this increase is time. The other 10% is other stuff. Okay, good question. Okay, so let's go to 18, and I think we're at Andy. Thank you. Okay, so the goal now that we can analyze, if the calculator gives us this information, we now feel okay analyzing it. So the goal is to be able to get the calculator to do all of this. We've got points to plot, we've got an equation to find, we've got a graph of a line, and then we've got these R's, and maybe we're going to extrapolate and predict populations in 2009. So is there anybody that does not have a calculator, a graphing calculator with them right now? Yours is dead, okay. Anybody else? 2 people? Everybody else has one? Okay, Eliza, do you know where my office is? Serge, do you know where my office is? Okay, it's just, it's 409. Just start walking around and makes a few rights. Just grab 2 of the graphing calculators off of the filing cabinet, please. Thank you. All right, so while Eliza is doing that, we will start working through the directions here. And I will say this, number 1, it's oftentimes very difficult for one person to get everybody at the same place on new calculator stuff. Some people are really quick. If you make a mistake and you type in something wrong, all of a sudden you're like 3 commands behind the rest of the class. So I will say this, if you ever fall behind, I am recording, I am making a video, you will see every single button that I click and it's fine. Furthermore, if you prefer looking at text and watching the video, here's the process written out step by step. We're not going to read this together, I'll just explain, but it is all written out in English here, okay? All right, so let's give this a shot. First thing we want to do is type in the data. So with the calculator here, first thing to do is go into stat, which is right up there. Everybody see the button that says stat? Thank you. Okay, so we push the button that says stat, and inside of here we've got a few different options. At the top you can see it says edit and calc and tests. For right now we just want to edit, so either hit enter or hit number 1, and we come in here. Now, just for kicks, all right, so is there anybody that it doesn't say L1 at the top left? Raise your hand if it does not say L1 at the top left. Stat is right there, and then enter. Yeah, so first, is there anybody that does not have L1 up there? Okay, so just in case, yeah, so let me explain how to clear data, because you'll want to be able to clear data. So if you guys just type in, like, for example, 5 and then enter and then 3 and then enter, just put a couple of random numbers in there. I will show you a couple of ways to clear the data. Number 1, you could arrow up and down and just hit the delete key, and it will delete one number at a time and bring everything else up. If there are 100 numbers in that list, would you want to do it that way? No, there are better ways. Let's put the 5 and the 3 back in. Okay, another option is to go all the way up to the top. Now it gets risky up here. If you push the delete key, you will be deleting the entire list, which seems like what we want, but you will also delete the name, which is called L1. And I don't really want to delete the name called L1. So what you do is you hit clear, and then you hit enter. And all the numbers go away. Fair? If you delete L1, so I will go up and accidentally delete L1, and you can see the list is gone, but the entire name is gone. If you hit stat, the bottom choice right there is your best friend. It says setup editor, so either scroll down or just hit 5, and then hit enter, and I think it will bring the list back. Good. Okay, so now we need to actually type in the data which is in that chart over there. We don't want to type in 1,930. We're just going to type in what? Just 30. So go ahead and type in all the numbers in the chart. You can hit enter and just do all the X's, or you can scroll to the right and do X and Y's together. Any questions on typing in the data? Everybody sees why there's 100 at the bottom of my list? What year was that? 2000 from 1900, that's 100 years. Okay, if you finish typing in the data, just stop touching your calculator so I know. Okay, and so while people are finishing the data, I'll say the next step is to get the calculator to plot those points. This step has a lot of steps in it. I will also say that when you take a quiz or a test, I would encourage you to write down any of these steps in plain English if it's something you just don't have memorized, right? If you do it enough times, you'll just know where the things are. But until then, feel free to write these on a note card or on the reference sheet. Okay, so what I'd like to do next is see the graph, the plot of those things. So can you guys go into y equals? And if you have anything in there, you know, like maybe you still have some function from the test, just clear it. I don't want to have anything graphed in there. We're just going to clear. And the next thing to do, once this is clear in here, is push the up button, which seems quite strange because it feels like we're already at the top. We're at Y1. But if you push up, you see it actually goes, there's some stuff up there at the top. Plot 1, plot 2, and plot 3. Hit enter right now. And plot 1 is now highlighted. Yes, it's a solid black color. Everybody see that? You push up, hit enter, and now plot 1 is solid. Now it's possible we might have to tweak some things on some of your calculators, but we'll get to it. If we get a mistake later on, we'll fix it. Next thing to do. All right, so in theory, these dots are now plotted on your calculator. The issue is that normally the window is like minus 10 to 10 and minus 10 to 10. Is that going to help us with these enormous numbers? No. So you're not going to see anything unless you really think about the window. You have two choices. You can change your window inside of the window screen so that it fits all of the data in the calculator. There's actually a really nice command where we say calculator, find the dots, and it's quite good at finding the dots. So I want to show you where that command is. If you go into zoom and then scroll down, so we hit the zoom button at the top, and we scroll down until we get to number 9, which says zoom stat, which has to do with statistical stuff. That's what we're doing. And if you hit enter, if everything is set up right, then we should see the dots. It's okay if we don't see the dots, but let me know. Is there anybody who does not see the dots? Zoom 9, zoom stat. Questions at this moment? Okay, that zoom stat is an important step because I know that at least some person, not necessarily somebody in this room, is going to come up to me in the quiz and say, I can't find the dots. I hit graph and there's no dots there. And it probably is just that you're not looking in the right spot. The dots are there, but they're just way off the screen. So zoom stat is your friend. Next thing to do is to ask the calculator to actually find the equation of the line. So what we're after is somehow I got this data right over here. This is how the calculator found the best line possible. So here's how we do this. Go back into stat. Where did we go before when we were in here? We went to edit. We're going to go to the right. Hit the right arrow and we're going to go to the calc menu. And there's a whole long intimidating list of foreign looking commands, but which is the one that looks familiar? Number 4, we're looking for linear regression, linreg. So either scroll down to number 4 or just hit 4. It brings you back to the home screen. And we could just hit enter. And if you just hit enter right now, and if we've done everything right, you should get exactly that screenshot. Okay. It turns out you don't need to. If you don't put anything, it assumes list 1 and list 2, which is a nice shortcut. I learned that shortcut from one of my students last semester when I taught 107. So a couple of folks don't have the R's. We can fix that. Derek, is that your issue too, or do you have? Okay, so here's how we get the R's. You only have to do this once, and your calculator will remember until you undo it. But just for the people that don't have the R's, we'll fix it. Sam? Yes, we were going to do that. yes, I would like to do that. At the moment, we have only the equation. But it's not going to graph anything because I didn't tell it to graph the equation. It's just the dots. So Sam is predicting the next step, which is how do you get it to graph that thing? We know what the equation is, but we want it to graph it. But first, let's help out the folks who don't have the R's. So if you have the R's, you don't need to do this, but if you don't have the R's, hit the yellow button in the top left, the second button, and then right above the 0 is the word catalog. That is what we want. Hit the 0. Now what we need to do is find the command that says diagnostic on. You can scroll down, it's all alphabetical. Catalog, you do second 0. So scroll down to find diagnostic on, but easier is to hit the button that says a D right above it, and it will jump you down to the D's. So if you just scroll and eventually find diagnostic on, and just hit enter, and then hit enter, the next time we find the linear regression, it will give us the R's. Yep, so scroll down until you find diagnostic on. Yep. One more. That's it right there. Hit enter. Hit enter again. Okay. All right, here we go. So let's ask it for linear regression again, but this time everybody should have the R's. So if we go stat, to the right, number 4, enter. Is there anybody that doesn't have the, so we just did the same thing we did before, stat, scroll to the right, hit number 4, and hit enter. And that brings us up to R's. Is there anybody that doesn't have the R's? So hit the stat button. Yep, scroll to the right, hit number 4, which is linreg, hit enter, and it gives the same numbers, including the R's. So again, you never need to do the diagnostic on again. It will remember, and you'll always have the R's. Okay, so one table is very excited at how to get the thing to graph the actual line. So let's bring everybody in on this. So here's how we do it. What I'd like to do is the same linear regression command, but I just got to tell it a little bit more. So here's how we do it. Hit stat. Okay, we'll fix that. We'll fix it. Okay, we're hitting stat, we're scrolling to the right, and again, we're choosing linear regression, which is number 4. So get your screen to say that, but do not hit enter. Okay, so we should be good now. Where are the R's?
Oh, how'd you get that?
That's why they pay me the big bucks. Stay right there. Okay, does everybody have this thing on the screen? Do not hit enter yet. We need to tell it something more. Okay, what I'd really like to do, you don't need to hit this button. What I'd really like to do is to get the equation of the line into the Y1. That's where I want it to go. So from this home screen, I need to tell the calculator to put the thing in Y1. So here's how we do it. It's kind of buried, so just follow along here. Hit the button that says VARS, which is right here. Vars. Scroll to the right to get to the YVARS menu. The very first option is function. That's the one you want, so hit enter. Function. And then the very first option is Y1, hit enter. This is what you want the command to look like. If your command looks like that, hit enter. Serge, you got it? You know where to find Y1? Go ahead. Tyler, you got it? Super. That is written in the text, yeah, in the packet. Okay, if it says this and you hit enter, it's going to give you lots of information you've seen before. It's exactly the same numbers we had before. But the nice thing is if you go into Y equals, what do you see? You see the equation of the line. 3,544x plus 36,943. And now if you hit graph, it will show you the line. Any questions on any of those steps? My goal is not to make you memorize like 700 different calculator commands. Feel free to write down any commands you need practice with on a reference index card or on, like on a reference sheet for the next test. But like I said, yeah, all of tonight's homework will be this. Yeah. Do we have a quiz coming up? What do we have? The quiz is on Friday. Yeah, the quiz is on Friday on equations of line. Here are 2 points, find the equation of the line that hits them, or here's one equation of a line, find the line that's perpendicular to that one, and then the second class is this one right here. So yes, we are going to do a linear regression thing on the quiz. Let me just look at something real quick. I will say that on Friday's quiz, yes, it will be about linear regression, but I am not going to ask you to do any of the commands that we've talked about today. I know this is very new for a lot of folks, and I don't want to stress anybody out about all these commands. What I am going to ask you to do is take a look at some screenshots that I've already done the linear regression for, and then do all the analysis, okay? Everything that followed those 2 screenshots, that's what's going to be on the quiz. I'm not going to ask you to use the calculator to do any regression. On the test in like a month, I will ask you to do a regression. Okay, last thing I wanted to do was get the calculator to help us answer this question. We wanted to know what the population was in 2009, okay? What's the population in 2009? Here's what we're gonna do. Looking at this screen right here, let me just check something out real quick. Okay, do you guys see, go into window for a second. What's the biggest X value in this window? Is 107. What was the X value for 2009? Was 109. If I want the calculator to predict 2009, I need to at least put 109 in here. I'm going to go ahead and put like 120 just to make sure it's definitely bigger than the 109. So everybody change that X max to 120. Doesn't matter to me. If you want, you can change them. And now we'll hit graph. And so this is just going to graph the line a little bit further to the right. It's no problem. It goes off the screen. It's okay. What I'd really like to know is how much is the population in 109? So here's what we do. Hit the trace button. Type in 109. Oh, sorry. Scratch that. Let's try second trace instead of trace. I thought I was going to do a nice shortcut, but it didn't work. Everybody have second trace? The very first option says value. Hit enter on that one. It says how much is X. What was the X value we wanted? It was 109. You type in 109 and hit enter. $423,253. Is that what we got? $423,239. Let's take a look. But which one is more accurate? The one we wrote up on the board or the one the calculator just gave us? The calculator one is more accurate. The numbers that we typed on the like that we did on the board were all rounded. We rounded to the nearest whole number. So we made some errors just to make it easier to write down. The best way to do this is let the calculator do all the grunt work. You just need to know how to ask it to do it, okay? Any questions on that? Okay, what I would like for you guys to do, you have 16 minutes. There is, on the next page, this is page 10, bunch of examples of sets of data. So what you're going to do is you're going to find the equation of the least squares line using all of the nice little tricks we just learned. You're going to decide if the line is good or not by looking at the picture. And you're going to interpret the slope and the y-intercept using a sentence in plain English. So I would encourage you to maybe split up the work, and maybe Tyler and Andy, you can join that table in the corner. So there are 4 people at that table. Maybe one person at each table can do part A and somebody else can do B. I don't need everybody to type in a million different things. But what I would like to happen, can you guys just focus for 1 second here? What I really like to happen is that once you have typed in your data set, show everybody else this screen on the right-hand side and let everybody write down the calculation, like all these numbers, okay? We don't need to do all the data entry, everybody. But everybody should get those numbers from your neighbors, and then you can interpret all of the different problems, all right? Last thing I'll say, I worked really hard, and it took a really long time to put up an answer key for this thing. I did not have this answer key last semester when I taught it. I'm giving it to you now. It took me a long time, so take advantage of it. Make sure you look through and you're getting stuff that's similar to what I have. Okay? Yeah, it's in the packet, just a page or two.